work or some of the work my group has done together with several collaborators. Let me switch to screen sharing. Okay, so you should be able to see my slides. So I will be talking about realistic virtual humans, how to generate them, how to animate them, and how to evaluate them. And so this is work that my group and myself have done over the past maybe five years. And it will be about realistic virtual humans. So if we have a look here, this is what I mean by this. So we see the real Felix standing in front of a virtual mirror. So what we see is not a real mirror, but a video projection where we see his avatar that we obtained by scanning. And the avatar does the same movement as Felix does because we have full body motion tracking and use this to animate the avatar. So the this whole project, or me working on avatars, started by the project IC Space, which stands for Intelligent Coaching Space. And this was a project in Bielefeld Center of Excellence on cognitive interaction technologies. And this was a huge interdisciplinary effort where our goal was to do sports training in virtual reality. So there were computer scientists involved, there were linguists, psychologists, biologists, and sports people. And the idea was to have, as you see here in the video that I'm going to start soon, idea was to have a virtual coach, and this coach instructs a real trainee to do certain sports movements, which you could imagine to be used in, I don't know, now we all sit at home in our basements, do sports online, or provide some rehabilitation training to people. So let me show you the video. So I turned off the sound, but you see that this coach, he speaks, he gives instruction, and you see Thomas in the virtual mirror. Because the mirror is virtual, we can also rotate it and to provide like different views, which might be better for training. And so this is the main idea. You have this virtual mirror. In the mirror, you see the virtual avatar. The avatar in real time does the same movements as the participant. And you have the intelligent coach who gives instruction and feedback on movement execution. So, but the project started in a like very simplistic manner. So we started from scratch. This was the first VR project that we did. So first we developed a low latency VR engine such that the delay between the movement of the real person and the movement of the avatar in the mirror is almost not noticeable. Otherwise, your sense of presence breaks down. And the avatars, as you see here, were like quite simplistic. But we were quite happy with the motion tracking in the mirror, so we gave this to sports people. And here you see Connie doing some cool yoga movements. And if you watch the mirror, you see that the foot of the avatar and also now the hands, they enter the ground. And this is in part due to OptiTrack's hacky motion tracking, but also because the avatar, the body proportions of the avatar do not really match the one of the participant. And once we switched to scanned avatars, this year showing an early version, so these problems do not show up. So first, your like motion tracking and motion mirroring through the avatar is more accurate. And second of all, we believe that if you have an avatar that really resembles you, also visually gives you higher sense of presence, more motivation, as I will show later. So how do we generate the avatars? Let me start with that. So for the realistic virtual humans, we have a set of requirements that we want to meet. So first of all, they should be realistic, as the name implies. And by this, we mean realistic in terms of the geometry and in terms of the texture. So there are many people who do more or less accurate geometry, but they don't put texture on top of the avatars, which then, if you are in a VR scenario like this virtual mirror and your mirror image doesn't have a texture, this looks quite strange. So we also aim for a high quality and accurate texture. So this is basically 3D scanning and reconstruction. The second requirement, the avatars should be ready to animate. So when we reconstruct the avatars, they should immediately be useful for the VR scenario that I just showed you. So we need controllers to deform body and hands. This is basically skeleton and skinning. But we also want controllers for face animation, like speech animation for the virtual coach, or eye animation, like gaze. And this is an important point because like scanning 3D characters is not that big of a deal right now. But then bringing it to a state that you can animate it requires rigging, and rigging oftentimes takes a couple of days. And we want to use these avatars in VR user studies where we invite people, we scan people, and then we want to put them in a virtual reality. And we don't want to invite them, scan them, send them back home, and invite them a second time a week after when the avatar is ready. So we have to be able to construct ready to animate avatars in like a couple of minutes. That's our goal. And then because of the low latency VR engine, rendering has to be really fast. So because of that, we opt for just a single textured model. So no multiple layers, like for instance, a skin layer and a cloth layer. This also means we cannot do proper cloth animation, so we don't even try. It's just one single textured mesh. So we need to scan people, and this is a video of our setup. So over the years, I kept buying cameras. We built this camera rig, which consists of 8 pillars of 6 cameras, so 48 cameras, which are synchronized by wire. So you press one button, they all take an image. And then from this, we can, through multi-view stereo, we can reconstruct a point cloud and textures. And because the human face is really important, we do a second scan, like a close-up snapshot using 8 cameras of the face. Now these cameras are all connected to one computer through USB. So we then download the images to this computer, run a multi-view stereo reconstruction technique, and get 2 point clouds, left one from the full body scan, right one from the face close-up scan, of like about 3 million points for the body and about 1 million points for the face. So now if you work in geometry and you get a point cloud, like the first thing you do is you press the Poisson surface reconstruction button in your software. Now, if we do this, we immediately see that this is probably not the right way to go. First of all, because we have all this garbage geometry flying around the avatar, which could be easily removed later. But then if I zoom in a bit and you look at the hands, there's basically only garbage geometry that we get out of it. Also because we don't get a very reliable point cloud for the hands because the details are just too subtle, and with our number of cameras, you cannot really reconstruct high quality hands. So that's a general problem. Also, other people had this problem. So when you reconstruct avatars from the point cloud the scanner gives you, and you do some kind of surface reconstruction, and you have missing data, then you have missing data, right? The avatar will not look nice in these regions. So we do what many people do, we exploit prior knowledge. We know that we are scanning a human. So we set up a human body template. Here we use the Autodesk character generator to produce such a template. It has about 20,000 vertices, so the resolution is sufficient for our purposes. It has a texture layout, which is important because we need texture. As you can see in the image on the left, it has a skeleton for body and hands, so we can also do finger movements. And it's also equipped with facial blend shapes, eyes and teeth, and everything you need, basically. But it doesn't look super human-like because the avatars or the characters in Autodesk character generator are more stylized. So we got a lot of 3D scans. So we got scans from the Max Planck Institute in Saarbrücken, Niels Hasler and colleagues, and the Max Planck Institute in Tübingen. And now in the meantime, we bought the Caesar database. So we have access to more than 1,000, like close to 2,000 full body scans. We fit our template to these scans. So we get basically 2,000 versions of the mesh topologies that we have here. And then we can do statistics. So we do a simple principal component analysis in this, like the space is 20,000 vertices. Every vertex has an X, Y, and Z coordinate. So every mesh is a 60,000 dimensional point in a vector space, and you do PCA. And let me illustrate this. So this is the mean mesh, so the average. And here are the 10 PCA dimensions. And this is basically the first principal component. So the strongest variation in the data, which is basically height, which is correlated to gender. So here we just throw in male and female scans at the same time. Second component is more or less body weight. And then, I know this seems to be more or less gender, and I know we have more components, so it's just a 10-dimensional approximation to the space of the to the data that we have. Meaning we can use 10 parameters to get a good approximation, good starting point to a human body shape. Now this model, we now want to fit to our data. So we have the template on the left, we have the scan in the center, and we want to pose and deform the template such that its geometry closely matches the geometry of the person that we scanned. Now, we are not the first to come to this idea. So this idea has been around for quite some time. For instance, the people in Tübingen, Michael Black's group, they do this like very successfully. But in the works I'm showing here, the like a bit older works, the simple model and variations of it, they don't have controllers for hands and face. And their model has been like machine learned from a lot of data. So if you don't have the access to the data and you want to have the same model, but with hands and with face, you're out of luck. So this is why we didn't use their model. It's also not that high resolution. But then in the meantime, so last year they published Simple X, so a model that, as you can see on the bottom, also has the possibility to do facial animation and to do hand movement or finger movements, as you can see here. And they can reconstruct this model from a single photograph. So basically the top is the input, the bottom is the output. And while this is super impressive, you also see it's not perfectly accurate, which you cannot expect if you input just a single photograph. But now we want to generate high quality avatars, meaning we want to reproject the images onto the geometry in order to get the texture. And if the geometry is off by a couple of centimeters, you will immediately see this in distorted texture. So we have to do more accurate fitting. So how to achieve this? So on the left, we see the point cloud in color and the template model that we want to fit to the point cloud in gray. The first step is we optimize for scale S, rotation R, and translation T, such that the two models closely fit. And the fitting term is just a sum of square differences of corresponding points, like in ICP, where we have the points in the scan, these are the P's, and we have points on the model, those are the X, and we have a couple of closest point correspondences, those are the C, so they are indexed by C. So we sum over all the corresponding points. They might be weighted, so if the user prescribes manually some landmarks, those get a higher weight than closest point correspondences that we automatically compute. And now we optimize scale, rotation, translation to map or transform the template to the scan, and the optimal solution you see already here. And it doesn't get better because the pose obviously is off. So let me write this in a slightly different way, where we have X, the point on the model, which depends on scale, rotation, and translation. Now, in order to get more accurate, we also have to adjust the pose. Basically meaning we have joint angles theta that we now also adjust. So this turns this into an inverse kinematics problem. So a nonlinear least squares problem that we solve. And still we are not terribly accurate because the overall body shape of the template still is the average human being, or here the like standard Autodesk generator template. But we have this 10-dimensional PCA that I showed you on the previous slide. So if we also use the PCA weight W, so the 10 sliders that we had on the previous slide, to adjust the body shape and the pose and scale, rotation, and translation, we already get quite close. So, and this is where many people stop, and this result would be okay for a couple of applications, but for our avatar generation, it's not accurate enough. So we have a couple bit of space on the right-hand side, so let's do one more step. And this step is let's say like out of model fine-tuning. If we say those are the model parameters that we have, this is also probably what you can learn through machine learning, because the number of parameters is rather small. But now in the last step, we optimize the position of all the vertices in our mesh, so all the 20,000 vertices. Again, the fitting term on the left-hand side here is closest point correspondences. And now, because every vertex is allowed to move, we need a regularization that prevents the model from doing like crazy stuff, like fitting too close to the noise or doing some other deformation that is not meaningful. So we use a discrete bending term here, and so bending is the change of mean curvature. The mean curvature is related to the Laplacian of positions x of the vertices. So as a first guess, as an approximation to the integral of the change of mean curvature, we sum over all the vertices, multiply by the Voronoi area of a vertex, and then as an approximation to change of mean curvature, we measure or penalize the squared deviation of the original Laplacian. This is the x bar. This is the one coming from the PCA optimization. And the current Laplacian. This is this x. Now this is, and would be just a quadratic energy that we can solve or minimize by solving one linear system. But as I will show on the next slide, this is not accurate enough. So you have to factor in a nonlinear term. And so because the previous one might be is not rotationally invariant. So in this nonlinear version, we say the current Laplacian should be as close as possible to a rotated version of the original Laplacian where we optimize, compute the optimal rotation on the fly. So this as rigid as possible deformation, as many of you might know. This is what many people do, and we deviate in 2 more steps. So instead of using the vertex Laplacian, we do the edge Laplacian that I will show in the next slide. And instead of minimizing squared deviation, so a kind of L2 norm, we go for an L1 norm. So why that? First of all, here's a comparison of the simple quadratic energy, or like a linear deformation technique, on the left, and the nonlinear technique with the proper rotation on the right-hand side. On the left, you have to solve one linear system. On the right, you have to do a nonlinear optimization, which requires at least one linear system for each iteration. So the right side is quite more computationally intensive, but the error also goes down by a factor of 2, which you see here in color coding. So if we want to go for accuracy, we should do the nonlinear version. Now the standard vertex Laplacian, this is shown on the left, where the standard is the cotangent Laplacian, where you have a center vertex, you sum over all the neighbors, and the weight for each neighbor is the cotan of the 2 angles that are shown here. But there's also the edge Laplacian, which has a 4 vertex stencil. It gives you a Laplacian vector for each edge, and is closely related to the vertex Laplacian. So if you sum the edge Laplacians around a vertex, you get back the vertex Laplacian. And it depends on the angles that are shown here. So we use this because then instead of a 2 norm for the vertex Laplacian or 2 norm for the edge Laplacian, we use a 1 norm. So we do an L1 optimization, or we use some robust statistical norm, because this allows few edges to have stronger banding than others, instead of distributing banding equally over all the edges as an L2 norm would do. And this allows us to reconstruct anisotropic wrinkles more accurately than the isotropic version on the left-hand side does, which is a subtle detail, but when it comes to human faces, subtle details start to matter. So we do this optimization and then get a reconstruction of the geometry. So you see the point cloud on the left-hand side, the reconstructed geometry on the right-hand side. So that's a quite good match. Now we then just reproject the 48 something texture photographs onto the geometry, and from the geometry to the texture. What you see on the left-hand side is the texture layout that we have, where the face eats up like a lot of space in the texture domain because the face is important, and you see the legs and the upper body and the arms somewhere distributed in the texture domain. But if you look closely, you also see that in the face region and in the hand region, something is wrong. Here's another close-up. And this is what I mentioned before, like the reconstruction in the face region is not accurate enough. So if the geometry is slightly off and we reproject the original images onto the slightly wrong geometry, the texture is off. And you immediately see this on like features in the texture or the geometry as the lips, for instance. But luckily, when you remember our scanning video, we didn't just do the photogrammetry scanning of the full body, get the point cloud, reconstruct the geometry, and do the texture. For that reason, that the face is important and has to be accurate, we also did the separate face scan, getting high quality point cloud of the face. And we also reconstruct the geometry here, get a separate texture for the face, merge the two to get the final avatar. So for the point cloud that we get from the face scanner, we take the model that we reconstructed so far, where the face is okay-ish, but not really super accurate. We do a rigid registration of this model to the face scan, and then do this fine scale non-rigid registration to get a more accurate geometry of the face. Then we also have to take care of the texture. So we get a texture from the body scan, we get a texture of the face scan, which of course only knows about the face and not about the body. And then we just merge the two using a face mask. So we know which region from this face texture we want to merge into the body texture. And we do this using Poisson image blending. And then we add back eyes and teeth, like synthetic textures from the character generator. Plus a couple of more details that I don't want to go into, like we pay particular attention to eyes and eyelids, teeth and tongue have to be adjusted, and so on and so on. But in the end, this is the avatar that we get. So let me zoom in a bit. So the face region is interesting, and so we get a quite good reconstruction. You see we have some texture artifacts along the ears. This is basically where hair was covering part of the ear, or where the geometry of the ear that we reconstruct is not perfect, but otherwise it's a quite decent reconstruction. Let me show you the hands. So the hands are difficult to scan, and we strongly regularize the geometry through the hand of the template, and then also use we have a couple of textures for hands, and we use the one that matches best. So this is not really the texture of the participant, because this is typically not accurate enough, but a texture of the template. So let's check our requirements. So here's another example. Let me again zoom into the face, because this is the most important part. And as you can see, this is like pretty accurate. So maybe we can check off the realistic requirements. Now, what about ready to animate? So by construction, the model has an embedded skeleton. This is the one that I showed you in the beginning that we start from. So if we have a skeleton, we can animate the character. So we can, I don't know, do like inverse kinematics and do any more or less meaningful poses, or I don't know, just use motion capturing on some real actors, record animations and play them back on the avatar. So they are, once we have reconstructed the avatar, they are ready for animation. So the second part is done. And I can render them in real time, because it's just a single, as we show here, it's just a single textured mesh. Now the important point is in the bottom left. The overall process, so we spent quite some time to optimize this, is less than 10 minutes. Now we are closer to 5 minutes. And this means we can really use this for user studies in VR. So we can invite people, put them in the scanner, and while the avatar is reconstructed, which is like mostly automatic, people fill out some consent forms or put on the markers for the motion tracking. And when they enter the virtual reality scenario, their avatar is ready. And this allowed us for the first time to evaluate the impact of personalized realistic avatars. So like previously, people did personalization of the face only, and the rest of the avatar is like looking like a stylized game character, or the scan quality is not optimal. And then, so we did this in 2007 when I just showed you the avatar reconstruction. We wanted to know how important is this really? So how much does it change your experience in a virtual reality scenario if you have your accurate scan as an avatar? So we analyzed the impact of these personalized scanned avatars. And we measured a lot of stuff. I'm just showing two. of these. So we analyzed virtual body ownership, which you can see to what extent do you have the feeling as if the virtual body is your body, right? So you enter the virtual environment, you look into the virtual mirror, you see this avatar, or if you are wearing a head-mounted display, you look down on your body and what you see is the virtual body, not your real body, because you have this headset. And the question is to which extent do you feel that this virtual body really is your body? And the second measure is the sense of presence. And this is to what extent do you feel present in the virtual environment right now? So how immersed are you in the virtual environment? And those two measures this is the standard that you measure if you do something with embodied avatars. And it's important to get high values for body ownership and presence, because what we want to do and what we are doing right now in a project is medical therapy in virtual reality. So we want to treat obese people here, but that doesn't really matter. But if you want to do some kind of therapy, people have to be immersed to get higher motivation and to get stronger effect sizes for the therapy. So this is what we want to analyze. How much do the personalized avatars help in this respect? So we did a user study with about 30 participants. And what we did is we scanned people and we gave them different avatars, let them interact with the avatars, and then used a couple of questionnaires to find out basically how well is body ownership and presence. So here's one example. So one avatar that we gave to people is like a stylized computer game avatar. And then we told people, we instructed them by audio to do certain movements like waving, as we see here. And then while they are waving, we instructed them to look at the mirror, look at their own body, look at the mirror again, look at the own body, and do this for a couple of movements. And like the different conditions is a stylized avatar or a realistic scanned avatar, but this is not the person, this is some other person that we scanned. So it's gender matched, of course, but it's a realistic avatar, but not their own avatar, their scan, or their scan. And this we tested in both a like cave-like environment that you see here. Of course, this would be with stereo glasses, but the video recording is just monocular. And in with a head-mounted display. This would look like this. And the difference between the two is that in the cave condition, let me go back to this, when you look at your own body, you see your real body, and only in the mirror you see the virtual body. In the head-mounted display, you don't see your real body. So when you look at the mirror and when you look at your body, you see the virtual avatar. Now, those 6 conditions we just we tested in randomized order, as you do for like proper user studies, and then ran all the battery on statistical evaluation. I will not go too much into detail about this because this is probably the wrong audience. But what we get out, just restricted to these 2 measures, body ownership and presence, is that we see an improvement in body ownership and in presence by the personalized avatars. And it's highly significant. So like this P is less than 1 promille, or like about 2 promille, but like a highly significant result. And so the question is, how strong is the result? And this is measured by this partial eta squared. And so this is a strong effect size if you're not used to this. So what we confirmed is that the personalized avatar in a statistically highly significant manner give you a strong improvement in body ownership and in presence. So let me come to the final part in my presentation. This is about character animation. So as I mentioned before, we now started a project where we want to do VR therapy for obese people by basically scanning them, putting them in front of a virtual mirror, and then with a slider increasing or decreasing the weight and letting them interact with their virtual avatar. Because like one of the main problems is that the body image, the self-image is slightly distorted in obese and anorexic people. And then the question is our animation realistic enough? So let me show you 2 examples to demonstrate that so far it's not. So what I showed you so far was linear blend skinning, and everybody who worked in skinning knows that, I know if you do this twisting transformations, you get the so-called candy wrapper effect that is not very nice, that you want to avoid. Because of that, people typically use dual quaternion skinning, which is like also super fast and kind of resolves these problems. But let me do another deformation. If we do something like this, you see like huge bulging here. So this would be the linear blend skinning result, which is, I know, a bit better in this respect. And we get this bulging for the dual quaternion skinning. Let me do another movement, like something like this, where linear blend skinning is this. And when we switch to dual quaternion skinning, so here we get loss of volume. Dual quaternion skinning, we get like increase of volume. Both is wrong. And the effect, so the artifacts are the stronger, the more volume your character has. So on a skinny character, these effects are less visible than on a character that has quite some volume, which is more or less the target group in our project. So we aimed at something that's a bit better. So when you analyze linear blend skinning and dual quaternion skinning, as you see here, the artifacts I just showed you, and then we analyze what kind of input data they need. And this can be a bit cumbersome because you need the model, you need the skeleton. Those 2 are easy. And you need high quality rigging weights. This is not so easy, but we more or less are used to this. The advantage is that those 2 methods are super fast, but you don't really get physically or anatomically plausible result as the artifacts on the bottom show. And you don't have secondary dynamics. Like if you move your, I don't know, you jump up and down, your belly chuckles or jiggles, this you don't get. And you cannot resolve collisions. So if the, I don't know, the hand touches the belly, it might penetrate, which is also not physically realistic, not plausible. So there are example-based skinning techniques. And as for instance, the simple or simple X model from Tübingen. And they are also very fast because they are an extended version of linear blend skinning. They give you very plausible result because they have been trained from lots of data, like many different people in many different poses. You can even put secondary dynamics on top. You don't get collisions, but the biggest problem is on the input side, because you need training data. And here this means you have to scan people in motion. So the simple setup that I showed you before that we have, it's not super simple, but it's like 50 DSLR cameras. Replace this by video cameras, then you get lots of data and the processing becomes much harder. So this is a problem when you want to train one of these models yourself. Then, of course, when you want to have something that's physically accurate, you can do a full-blown physics simulation, like the works here or the recent Viper approach. Those, of course, give you physically plausible results, by definition, more or less. You do get dynamics, you can resolve collisions, that's all very nice. But they are computationally quite heavy when you want to simulate a full character. And what we came up and think it's a quite good compromise is not frames per second, but fast projective skinning, which Martin worked on the last 2 years. And in particular for the setting that we are proposing, we think this satisfies all the requirements that we have. So how does that work? Let's say you have a character and an embedded skeleton. Then the first thing we do is we turn these skeleton lines into a volumetric skeleton where we have spheres for the joints and these cylindrical capsules for the bones. And then we establish a correspondence between the skin and the skeleton by starting off with closest point like projections and then smoothing this in order to resolve some intersections. And then we have a mapping from the skin to the bone, which allows us to shrink wrap the skin onto the volumetric skeleton, such that now every triangle that used to be on the skin has a counterpart on the skeleton. And we basically now have 2 versions of the mesh, one on the skin and one on the bone, on the skeleton. Basically meaning every triangle on the bone has a counterpart on the skin. These 2 form a volumetric cell, like a prism, which we can split up into tetrahedra, which we can use for simulation. So this is just a very easy way to get a volumetric mesh to use for elastodynamic simulation. For the simulation has to be fast and has to be robust. So we use projective dynamics, which is a method by Bostch and colleagues in 2014. It's a really cool idea. I don't have time to go too much into detail. If you don't know it, check it out. It's really nice. The main idea is that you formulate your cost function, your energies, as deviation from constraints. So every tetrahedron in our case gives us a constraint, and then you project the current vertices of the tetrahedron to the version that satisfies the constraint. And our constraints, for instance, are tetrahedron should not deform. And the elastic energy is how much does the tetrahedron deform? So how much does it deviate from the undeformed version? And for the current state X, you get the projection P. So P would be the original tetrahedron rotated and translated to match as closely as possible the current state. And then the difference between X and P is your elastic energy. So you do this for all the tetrahedra, which can be done in parallel. And then every vertex belongs to several tetrahedra. The ideal projections, they deviate, so the target positions deviate, and you have to solve a linear system to satisfy all the constraints in a least squares manner. This is the system shown here. This is the system matrix that consists of a mass term. This is basically responsible for inertia. This QQ transpose is least squares constraint satisfaction. We are looking for all the vertex positions X, and we have the right-hand side where the projected constraints like the target positions come in. So meaning for every time step, so what you see here is one time step of projective dynamics. For every time step, you do a couple of iterations, like 5 to 10 are typically sufficient. And for each of these iterations, you have to solve a linear system. Typically, if your constraint set stays the same, like you don't get additional tetrahedra or you don't delete tetrahedra or cut tetrahedra, then the matrix is constant. You can prefactor the matrix and just do a Cholesky back substitution here. And then this is really fast. It breaks down when the constraints change, because then the matrix changes, and then you have to refactorize. And this happens, for instance, if you get, if you have collisions, because every collision gives you a new constraint. So collisions are not really easy with projective dynamics. Unfortunately, we have collisions and we want to handle collisions. But let's say, so I don't know what this line here is. I didn't do it. Whoever was able to draw on my screen might please remove it. So now the skeleton moves, and if we start the simulation, then also the skin moves, because we do have the volumetric tissue in between. So let me show you on this example that the volumetric bones are important. So on the left, we see just the bone lines, as we typically do in mesh skinning, where the bones are just an infinitely thin line. And then if you have this rotation, a twist rotation from the hip, then if it's just the infinitely thin bone that rotates, it doesn't cause any elastic deformation in the volumetric tissue. But if we have a volumetric bone that twists, then this also causes the leg, basically all the tissue to rotate. So let me give you an example. So let's do the same two deformations that broke before. So here we have the candy wrapper effect. In linear blend skinning, it's somewhat better in dual quaternion skinning. And this is like projective skinning. That looks quite okay. So the second, let me do the leg. Okay, now I somehow messed up, but like dual quaternion skinning is this bulging, this volume gain. Linear blend skinning is volume loss, and it jiggles a bit because we don't have a previous state. The previous state was computed by the other methods. So this gives you quite good results. Let me play an animation that makes it a bit clearer. So this is the linear blend skinning. And then when I switch to this projective skinning, even if we have strong banding in the joints, you see that it works quite well. You also see that it's quite a bit slower than linear blend skinning, which is super fast. And the projective skinning is interactive, but it's not fast enough. And this is why we went for fast projective skinning. So this, we basically mapped it to the GPU, or Martin did map it to the GPU. And then the question is how to solve this linear system. Let's call it A times X equals B that we have to solve for each frame, how to do this fast. On the CPU, what you typically do is Cholesky factorization, but as soon as you get collisions, you have to refactorize and performance goes down. On the GPU, like Cholesky factorization doesn't map very well to the GPU. So we switched to preconditioned conjugate gradients. And then what you have to do basically is a fast matrix vector multiplication when the matrix is sparse, and dot products, which are easy. So the sparse matrix vector multiply, this is the main thing that you want to optimize. And whenever you do something on the GPU, memory access and memory layout are crucial, in particular for dense, not for dense, but for sparse matrices. So Martin came up with a new representation for sparse matrices that beat Q-sparse by a bit. So Q-sparse is very good if you have very large matrices, but for matrices of moderate size like we have, it's not super efficient. CRS is compressed row storage, and ELL is another standard format for sparse matrices. And our format, which is like a mix of the two, we get a quite faster implementation of matrix vector multiplication. And since this is the main ingredient for conjugate gradients, this speeds up conjugate gradient quite a bit. Second idea to make this faster, you don't simulate on the full resolution mesh, you simulate on a coarser simulation mesh, and then you upsample to a high resolution visualization mesh. And I don't have time to go into detail here, but what we use is moving least squares approximation, which is something that at least I learned from point-based graphics, but it's also used for meshless simulation in physics. And this allows us to do local least squares interpolations of the local fine resolution vertices are represented as linear combinations of the coarse vertices in a nice and smooth manner. So this is our skinning technique. And now, because we do conjugate gradients, we don't depend on prefactorization. We can also do collisions. And here are two like more or less realistic examples where you see that without collisions, it looks strange. With collisions, it looks strange too, but not that strange. But like seriously, you want to have collisions, and here's like another example. We detect collisions on the CPU. This is just fast enough. So we do some load balancing between CPU and GPU. And then we resolve collisions by just adding constraints to the projective dynamics simulation, which changes the matrix, but this is not a big deal for a conjugate gradient solver. So we get a quite realistic behavior. We get this secondary dynamics, this jiggling, we get collisions. And for our characters, like you see on the left-hand side, that have about 20,000 vertices, we simulate at a downscale version and then upsample using MLS. And even with collisions, we get like 500 frames per second. So this is fast enough for our purposes. So the next step would be to include this into the virtual reality, virtual mirror environment. So let me conclude. So what I showed you is first avatar generation by fitting a template quite accurately to a point cloud. And like there's tons of ideas and opportunities for future work. Like we use about 50 cameras. It would be cooler to have fewer cameras, like one. So we are working on this, other people are working on this. So this would make avatars more accessible to more people. And in particular for like medical purposes, you shouldn't just use a single surface model, but maybe like volumetric anatomical body model, which a couple of people also did. So the question is how to generate in like a couple of minutes from few cameras a body model that is anatomically more correct than what we have. Then I showed you this fast projective skinning, which gives you physically plausible results in real time. And here the question is, does this still hold if you have a more complex, anatomically more plausible model? In the end, we did the evaluation. We could show that body ownership and presence are significantly improved when we switch to personalized avatars in VR scenarios. Now, what we did not test so far is how important is this physics-based animation? So when you put people in front of a virtual mirror, does it really make a difference if you have linear blend scanning with all the artifacts that we've seen, or if we switch to this physics-based animation? So currently it's a bit difficult to do user studies, in particular wearing a headset and sharing this headset with participants. So this will take a couple of time once we can do this evaluation. But let me also give you a more like general conclusion. So what I showed you is like lots of geometry. And so my statement is like geometry is everywhere. It's not really my statement. Like Kepler already said, like ubi materia, ibi geometria. Geometry is really everywhere. So if you work in geometry processing, you will not run out of problems. But we also need physics, and we need physical models for dynamic characters that are robust and efficient. And I didn't find a good quote, but like obey physics, it's the law. I don't know who to cite here, maybe God, but I didn't know what year it was. And the third ingredient, like geometry and physics, the third ingredient is data. Like only geometry is not sufficient. Geometry and physics doesn't work because the stuff that we want to simulate is too complicated to do this in real time. We have to learn from data. Only learning from data also is not sufficient. So you have to combine learning and physics to find data-driven models that are regularized by physics-based priors. And this brings me to the conclusion of the conclusion, namely, in order to bring our field forward, now everything we do is getting more and more complicated, and we have to share our work to enable other people to build on top of it. So if you have data and you are allowed to share the data, publish it. And if you have code and you're allowed to share your code, then also publish it to help other people to get started or to improve the state of the art. So if like other people hadn't published the human body scans, we would not have been able to do this work. So whenever possible, please publish data, publish code. And I just want to mention the replicability stamp initiative that was initiated by Daniele Panozzo and currently is run and organized by Marco Atene. Very nice initiative where you can, if you have a paper published at a conference or a journal collaborating with this, you can get an additional reward, the replicability stamp, if you make everything needed to reproduce your results accessible. So if you want to know more about the stuff I showed you, you find all of them on my publications page. You just have to remember the icons here. And for the fast projective scanning, we also have code available. So go and check it out and have fun. So let me end by thanking a couple of people, mainly my group. And what I showed you today is work by Thomas and Jascha, who did their PhD on avatar reconstruction. For full body, that was Thomas, and for the face, that was Jascha. Martin did the projective scanning and fast projective scanning, and Stefan is currently working on the VR therapy for obese people project. And I don't know much about VR, so when it comes to user studies and stuff like this, we collaborate intensively with the group of Mark Latuschik in at the University of Würzburg, and Andrea and Daniel are two of his employees. Thanks to people who publish data, and for all the participants that let us scan them, and thanks to people who gave us money, and thanks to you for your attention. And I'm open for questions.
Okay. Thank you very much, Mario. So if anyone has a question for the presentation, please.
So I see two questions in the chat. Let me just read them. Currently, the method fits a 3D model to body and cloth, while cloth deform. Do you think it would be an interesting direction of future research to find the underlying geometry of the naked body under cloth? Yes, that's a very good point. So our scans work okay-ish, or like work as well as I showed you, if people wear rather tight clothing. If you have white clothing, our scans don't look nice. So it's in my opinion, really good idea to you scan people and then you somehow separate cloth from body. People are already doing this. So Gérard Ponsmol, who's leading a research group at the Max Planck Institute in Saarbrücken, he did a couple of work on this. Because then once you have the separation, then you can also do cloth simulation when the body moves. So this gives you much more realistic results. So that's a good direction to proceed. And then we have a second question. All our examples are for bipedal characters, and whether it works for characters that have more legs. Yes, I think so. There's no assumption that we just have 2 legs or 2 arms. You just have to provide a character mesh. It doesn't have to be nice and closed, just a mesh and a skeleton. And then we do this shrink wrapping and generate a volumetric mesh. And it shouldn't depend on the number of legs. And the code is online, so you can try.
Okay, any other question? There's another question by Ram Nathan.
Yeah. So in the template-based reconstruction, the number of vertices seems to be less, around 20K. What is the maximum number of points? Oh, I think the maximum number that we tried for the template reconstruction is 20K because this is our template mesh. But I think there's no limit. It's just if you have more vertices, you have to wait longer. And if you need more geometric detail, I would go for a multi-resolution or subdivision approach where you fit a coarse mesh first, because this is fast and probably more robust, and then subdivide the mesh and refit and subdivide again. So we did one step of subdivision for the faces. So this is a paper at VMV, Vision Modeling and Visualization, in 2015. This is where we looked at accurate reconstruction of the face. And there we did this approach, so coarse mesh first. And when the fit converges, we subdivide once and refit. But this you can also do a couple of times if you want to have a higher resolution. But our maximum resolution was 20K because it was sufficient. Any more questions?
Any question? There's a question from Loic.
Which variety of secondary effects can we get? I mean, the model that we use in projective dynamics is this isotropic elastic deformation of these prisms that are spanned between every triangle on the skin and its counterpart on the bone. So this is like anatomically, this is not really accurate. So we don't even have a rib cage so far. So this is obviously wrong. We are working on an extension to get a more anatomically accurate model. But in terms of physics, so we have, this is isotropic elastic deformation. And then we get all the, like the jiggle is just standard inertia. We don't have anisotropic deformation as like you have in the Viper approach. So this is something we do not have. We should get volume preservation and standard elasticity, but nothing anisotropic. But like anything you can put into projective dynamics, you can use to extend our approach.
Okay. Any other question?
Oh, that was one. Let me catch up. So regarding learning and data, is it mainly to address computational efficiency? Yes, I would think so. If we have sufficient time and patience, we could probably model the problems that we want to simulate in a physics-based manner and just wait a day or two to animate a character. But since we are doing graphics and many of us are doing real-time graphics, we have to speed it up, or we don't have enough knowledge about how the body really deforms in an anatomically plausible way, and then we just learn it from data or do some combination of the two. And then there's one more question about the accuracy of the reconstruction. How to answer that? So the problem is we don't really have ground truth, because we could use a statue that we scan with a laser scanner and then compare that result to our photogrammetry reconstruction. So that's a question that I cannot really answer, what the accuracy compared to a ground truth that we don't have is. So we just measure sum of squared distances of the model to the point cloud, but the point cloud is noisy, so you don't really want to fit perfectly. You have to have a regularization, which is our banding term. And then one more question: how long does it take between having the subject scanned and the avatar ready to use? This is when we published, this was less than 10 minutes, and now it's somewhere between 5 and 10 minutes. From person enters the room to avatar is done. So including scanning, downloading the photos to the computer, which is taking quite an amount of time, and then the reconstruction. And this is done on a standard computer with a powerful CPU.
Any other question? Okay, so I have a very last question for this presentation. So you mentioned about computation time. You mentioned about the reconstruction is between 5 and 10 minutes, right? Mm-hmm. And then, so how much time for manual work? Because I guess when you get the body from the scan data, you have a mesh. I guess you have to place or locate the feature point manually. So amount of manual work, I mean, concretely, among these 5 to 10 minutes, how much manual work does it need to reconstruct one scan?
Mm-hmm. So what we have to do is the user clicks a couple of landmarks on the point cloud in the order of 10. So we click points on the hand, like 1 point on each hand, a point on the feet. And because the face is important, we click some points on the eye and mouth region. And I would say the manual work is about a minute. Mm-hmm. And the rest is just downloading the images, reconstructing the point cloud, then the manual clicking, and then the reconstruction.